Welcome back, everybody, for the second session for this morning. Last night I was trying to figure out how to kind of tie this all together, what this session's about. The first thing that popped into my mind was like, well, at least it'll be light on graph theory, so nobody will have like that pained look on their face like I probably had on my face yesterday. Then I was sort of watching the documentary on the Large Hadron Collider last night on NOVA, and I was like, kind of interesting to see Peter Higgs there. 40, 50 years ago, he theorized that there should be the Higgs boson, and it took CERN and billions of dollars to be able to find that particle. And it was kind of interesting. I thought, well, that's an interesting analogy to what we're trying to do here. There's this particle that they're looking through, sifting through, like all this tons of data. How do they store that data? How do they find that sort of thing? And so this morning's session, this session is on storage challenges. And part of the thing that I think the role in my analogy that Peter Higgs plays is the management and people that are trying to sell this whole, hey, cloud computing. Just stick everything in the cloud. Everything will be magical. It'll be free. It'll be great. We'll find everything. You just have to stick it into the cloud. Well, that was the theory part of the Peter Higgs. The reality is the billions of dollars and all the countries and all the scientists that actually took to do the investigation to actually prove out that the Higgs boson existed. So what we have here is our speakers will talk about what is the actual cost, what is the engineering cost to be able to do cloud computing, and what are some of the storage challenges we have. Our first speaker up today is Tim Barr. He is a senior subject matter expert for CyberAnalytics and Intelligence segment at Cray. And he will be talking about enterprise data storage and analysis. Before he was at Cray, he was a chief architect for General Dynamics working with DHS. So definitely familiar with the spaces that probably a lot of us play in. So, Tim?
Okay, thanks for the introduction, and hopefully everybody had a chance to grab coffee and donuts. So we'll be nice and energized for this. So we'll jump right into the agenda. So some of the things we're going to cover today are some of the challenges in big data analytics. So this is going to be probably a little bit more generic than Flow specifically, but we're going to cover some of the current challenges. We're also going to touch on the topic of why many Hadoop deployments underdeliver. Chose not to use the term fail there because ultimately, really what we're seeing in the market today is that a number of organizations that are experimenting with Hadoop, they're getting some incremental value out of it, but they're not necessarily realizing the full value out of the stack. We're going to delve into what Apache Spark is, into the core components, the SQL, streaming, machine learning libraries, and GraphX. I've got a few slides that talk about graphs for CyberAnalytics. This topic has been discussed a little bit this week. So there'll probably just be a couple things that I'll point out on those slides, and we'll move through those fairly quick. I've also got have a slide that deals with a hybrid Spark architecture. Ultimately, when you're looking to deploy tools like this, you want to you want them to be complementary to things that exist within your architecture today. Last thing that we've got will be kind of a quick coding example on the Scala programming language and why you should love it, and it's yet another awesome programming language that will solve all of our problems. All right, so challenges in big data analytics. One of the things that we're seeing is, the maturity of, it says Hadoop today down at the bottom. It's, it's probably more Hadoop yesterday. Really, it's kind of that batch focus. It's the MapReduce, doing things like ETL, indexing, aggregation, and summarization of your data. Really, what we're seeing now is the emergence of that low latency analytics that need to occur on things like streaming data, Twitter data, event logs, the Internet of Things, business intelligence and the like. And really what we're talking about is we're talking about moving response times from minutes down to milliseconds. And Apache Spark is a great platform to help do that, given the fact the focus on storing data in memory and then the ability to kind of quickly traverse those data sets. So, up in the top right corner, we're kind of highlighting that, the performance really is gained by, a creative memory and storage hierarchies. So that's Spark in and of itself. So one of the things we talk a lot about is the time to analytic value. Kind of what we've laid out here is kind of an atypical waterfall process on deploying a big data Hadoop type solution. So, you stand up and you build the big data cluster. You spend a fair amount of time ETLing and moving data onto the platform. At some point, there's data preparation where you're going through cleansing data, maybe removing duplicate data, things like that. And then that point where the analysis actually starts. Really what we're seeing is that the time to analytic value for most organizations deploying solutions on Hadoop are taking way too long. Ultimately what ends up happening is it becomes an exercise in moving the data warehouse off of your expensive data warehouses vendor's platform into Hadoop. You start to write the MapReduce reporting jobs, and really the only thing that you've done is you've moved your business intelligence reporting from one platform to another. It's really not adding any new analytic value. So we have this concept of integrated advanced analytics. Really, we see that the tasks across the very top list, across the very top, data preparation, basic profiling, statistics, machine learning, and streaming. These ultimately map down to three kind of key areas. It's batch analytics, which I think we're all familiar with. It's kind of the MapReduce paradigm. Iterative analytics is where we get into kind of that ad hoc machine learning streaming types of focus, and then we have the interactive queries. I think any analytic solution that you're looking at needs to be able to support these functions. The machine needs to be doing something for you when you're not when your hands aren't on the keyboard. So that's where things like streaming and machine learning can add a lot of value in your analytics process. Okay, so why do Hadoop deployments under-deliver? One of the key things, and it's actually probably not as relevant for this particular community. One of the things we're seeing is that data scientists are absolutely critical to the process, and they are in short demand. The good ones are. We hire a lot of these people. I can tell you, I have a very hard time finding good data scientists. There's a shortage of big data tools, and by that we mean not necessarily tools to store and analyze data. There's a shortage of front-end tools that kind of ease some of the adoption of trying to do analytics on these platforms. MapReduce in and of itself is if you've ever written a MapReduce job, it's a bit of an ugly language to try and engage with and get some form of value out of it quickly. Next bullet was the complexity of the MapReduce programming environment. The cost of the analytic value is currently too high. We kind of touched on that already. MapReduce, ultimately, given the performance of MapReduce on Hadoop environments, it really doesn't allow the analysts to kind of follow their nose. We talk a lot about data discovery, and data discovery is a process where an analyst or data scientist really digs into their data and they start to ask questions. And ultimately, if those questions are taking too long to get responses, it's hard for the analyst to kind of follow their train of thought. So really, what you need is systems that kind of think as quickly as the analyst thinks. Because it's not that I need to ask one big question and 23 hours later get a response back, and then that's the holy grail response. Ultimately, what happens is I may ask that question, 23 hours later I get a response back, and that wasn't what I was expecting at all. I now need to reformulate that question and ask it again. So those response times of hours is not acceptable for the types of work that you guys do. One of the last bullet is actually very specific to Apache Spark. Spark is gaining a lot of momentum right now. It's in the media a lot. There are a lot of people that are kind of playing around with it. One of the biggest problems that we see, though, is that people will take Spark and install it on top of an existing Hadoop deployment that they have. That Hadoop deployment most likely is on a set of hardware that's already reached end of life. It happened to be a few 5, 6, 7 spare servers that they had access to, were able to play around with. So what ends up happening is that architecture for those machines, they tend to be underpowered from a memory perspective. The processors are typically a couple of generations behind. The disks are not quick enough to keep up. So ultimately, what you have is you have a very bad experience with something that should be helpful in solving a lot of problems. Apache Spark is not Hadoop. The system requirements are extremely different for these types of environments. Spark likes to have a really beefy server, a lot of RAM, lots of CPU cycles. So if we're not taking that into consideration when we're building out our Spark cluster, we're going to suffer from performance. So the other challenge is Spark actually does a really nice job of when it runs out of physical RAM, it has the ability to swap off the disk and read data off disk. That in and of itself is a challenge when we start talking about performance. It creates a tremendous degradation in performance. Okay, so I put this in here. It was a Forbes article a while back. Mike Driscoll, CEO of MetaMarkets, he had an interesting quote. The article was entitled "How to Avoid a Hadoop Hangover." The first sentence is really key. Hadoop is hard to set up, use, and maintain. If you've ever tried to build out a cluster from the ground up, it's a daunting task. Once it's up and running, there's a maintenance and monitoring aspect to it that somebody has to do. So you have to get familiar with these tools and really understand them, and they're quite a bit different and quite a bit more complex than some of the other types of databases that we've used in the past. So perception versus reality. In the market today. So again, this is kind of my perspective. It covers more than just CyberAnalytics, but Hadoop is synonymous with big data. It's capable of huge scale with just ad hoc infrastructure. We have a lot of conversations with at Cray with with customers that range anywhere from government, intelligence, commercial customers. We even have a Major League Baseball team that's a customer. So we talk a lot. We talk to a lot of folks that are really doing analytics across a wide spread of use cases. What we're seeing is that a lot of people are experimenting. They have a cluster set up. They're typically doing some data warehousey types of things in there. There's some reports that they used to run that they're now maybe running off of the Hadoop platform. We talked about the data scientist bottleneck. Again, for this community, I don't see that as much of a problem, but in other areas, data science and the lack thereof is a huge problem. We're seeing a lot of momentum, with the academic groups that we work with, as well as the government and commercial is where it makes sense is jumping on board as well. Hadoop is widely perceived as high potential, not yet high value. That's one of the things that we're hearing quite a bit. All right, so we're going to shift gears. We'll talk about Spark now. So Spark, in and of itself, so it's it was born out of UC Berkeley, the Berkeley data analytics stack. It is a distributed data analytics engine. The core engine itself provides kind of the platform where it supports the ecosystem supports streaming, SQL, machine learning, and graph processing modules. You can write code and program in Python, Scala, or Java. So you have a couple choices there. As far as programming environments. Okay, so at the core Spark, I'm going to go ahead and just load all these here. All right, so at the core of Spark is something called the resilient distributed data set. It's a distributed collection of objects. So these exist in memory. They're built via transformations that you write into your code, and they're automatically rebuilt on failure. So there is a level of fault tolerance there. The great thing about RDDs are that they can read data out of HDFS, out of HBase, out of databases that you have. They can read data off disk. And pull that into memory and create that RDD object. So you create it. You can create it at runtime. You can create it ad hoc if if there's a level of analysis that you want to do on a subset of data, or you can have RDDs that are more encompassing, where you're doing things like graph theory, against your larger data set. That's really important because a lot of the solutions in the past have a lot of big data solutions really focus on kind of defining schemas to structure your data, and you get get locked into a format that ultimately, a month or two down the road, you have a new data set that you need to add to into the mix, and your schema doesn't support it, your indexes don't support it, things like that. So this really gives you an incredibly flexible platform to kind of keep that data stored down in HDFS, and then as you need it, you kind of pull it up into an RDD. And in that process, you can actually do transformations on it as well too. So if there's, if it's key value attribute pairs that you want to structure the data in, you can do that. If it's more of a traditional, SQL schema-driven RDD where you want to structure it more like a table and do analytics that way, it'll support that. And again, you're not really locked into any one particular format when you do this. Okay. So the benefits of a unified platform. The nice thing with Spark is that given the fact that it natively uses HDFS to kind of store data, you don't have to copy and ETL data all over the place across your network. This has been a huge challenge. You guys are intimately familiar with it. At Cray, it's a supercomputing problem. Is moving data back and forth is not a small task. You can combine processing types into one program. Code reuse. This is something within Spark we really want to highlight and kind of emphasize this point is that you can go in and write an ad hoc piece of code, a piece of Scala code that you then take and reuse and plug directly into say your streaming module. Doesn't require any rework of the code. You don't have to redo anything in there for that to work. These things save time. And ultimately, what that results is, you have one system to learn, one system to maintain, and really the focus is kind of on simplifying the architecture, not making it more complicated. All right, so Spark SQL. So there's this concept of creating unified data access with schema RDD. So the schema RDD is nothing more than it's a table that you represent as a schema plus the data itself. It does have compatibility with Hive. So if there's some Hadoop already within your environment and you need to integrate, there are ways to do that. You can also connect via ODBC and JDBC. So if there are other visualization tools or other things that you use within your environment, you can plug it directly into here. I mean, the reality should be is that anything that you're looking at for analytics solutions, they shouldn't be a rip and replace or a complete swap out of something that you're doing today. It should be complementary to that architecture. All right, so Spark Streaming. What it does is it expresses streams as a series of RDDs over time. So you can combine streaming and batch techniques. So again, that kind of gets back to that code reuse point. These are stateful and fault tolerant. So much like many other things in the Hadoop ecosystem, it's built to fail. It knows it's going to fail at some point, so it's fault tolerant. So it can recover from failure. Inputs and outputs. So out of the box, Spark can take data from Kafka, Flume, HDFS or S3, Kinesis, Twitter, and then it's able to transform and output that data out to HDFS, out to a database, or if if there's some form of a dashboard that you're using for monitoring. This is really important. A lot of these, a lot of the day-to-day things that we do, you can write streaming code to kind of handle kind of filtering and sifting through data as it's coming in, and you're really seeing kind of quick performance on that as well. All right, so machine learning, iterative computation. So the concept of the RDD vector, which is vectors and matrices. I've listed out some of the current machine learning algorithms that are part of the MLlib 1.1. So within flow data, things that are helpful: k-means clustering, linear SVM. These are things that are built into the package. So you don't have to go off and create custom machine learning algorithms. These are there, ready to be leveraged, and it gives you a couple of steps ahead when you're starting to write your code. So the GraphX module, so unifies graphs with RDDs of edges and vertices. So you can view this data as graph or a collection. So if there's data that you've loaded as an RDD for GraphX, you can actually run ad hoc queries against that as well too, and batch process queries against it. If there are algorithms outside of what they provide is within GraphX. You can write your own custom graph algorithms via the Pregel API. Current list includes PageRank, connected components, label propagation, SVD, strongly connected components, and triangle count. This list is fairly basic. I do expect, given the momentum behind development within the Spark community, I do expect this to grow. These are fairly basic. The extension through the Pregel API is available. It's not a terribly simple process, but you do have the ability to do that. Okay, so I'm only going to point out a couple things here. The graph in CyberAnalytics has been covered quite extensively this week, and these next two slides are going to be fairly elementary, I think, compared to some of the work that's been presented already. One bullet I'll highlight here is the fail fast, fail cheap. Ultimately, you should choose an analytics platform that allows the analyst to ask questions really fast and get responses back, even if they're failure responses, even if it's not the answer they expected. That's part of that data discovery analytics process that data scientists and analysts go through. Really, one of the analogies, there's an article that was written talking about, most data scientists are, they spend 80% of their job kind of acting as a data janitor. They move data around, they ETL data. They typically only spend about 20% of their time actually doing true data science or analytics against their data sets. We need to flip that. That should be the other way around. Really, architectures like this are meant to they're meant to flip that paradigm upside down so that 20% of the time is kind of pushing, pulling data, and then 80% of the time is focused on analytics and data science. Again, I'll highlight just a subset here, but some graph algorithms that we found helpful for analyzing flow data and CyberAnalytics data in general are subgraph identification, alias identification, shortest path, common node, clustering and community detection, and then there's just more of a generalized concept of having a graph-based cyber discovery environment available to your analysts and available to your data scientists. That's kind of a key point. A lot of the research that's been done is kind of focused on providing the output of some graph analytic to the analysts to then do research, but really providing them an environment where they can have a large graph and do discovery on that and get responses back in a meaningful time frame. That's kind of a key component, I think, to that analytic platform. General types of questions, you need a Swiss Army knife for those, but for specific, well-understood questions, it's an X-Acto knife problem. Okay, so I've got a couple slides that deal with the system requirements for Spark, and I really want to emphasize this point. If you take nothing else away from this presentation, it's just an understanding and appreciation for the fact that when we build clusters to run Apache Spark, the system requirements are vastly different than normal types of Hadoop environments. Storage system. It's recommended that you run Spark on top of the nodes that you're running HDFS on. Again, this is dedicated to Spark. Ideally, you don't want this to be a shared environment where there's other Hadoop MapReduce types of things going on. These need to be dedicated clusters for this purpose. Local disks. Recommend 4 to 8 disks per node. You need to have a decent amount of storage there. You want more spindles. Helps increase the I/O, the number of spindles. The size of the disks themselves is a little bit less important that we go with large disks. The number of independent spindles tends to make more of a difference. Memory. This is probably one of the key points and one of the biggest bottlenecks that we see is that they recommend starting anywhere from 8 gigs up. I would say put as much memory in the box as you can afford. You will not regret the decision at all. Network, a lot of Spark applications are network bound. The example I was referring to earlier where, you've got some end-of-life equipment, it's typically probably giggy connected, slow network, it's got slow disk, not a lot of memory, aged processors. 10 gig networks, this is kind of the standard, this is the norm now for Spark clusters. We're starting to see InfiniBand backplaned Spark clusters, dedicated InfiniBand networks just for the Spark cluster itself. It helps alleviate some of the network congestion as the system is communicating. CPU cores, this is another area where, depending upon the complexity of your analytics, you want to invest heavy here. They're recommending at least 8 to 16 cores per machine. Again, these are not your 1U pizza boxes that that your IT guys are giving you because they're left over and not currently performing a function. So HDFS, when we talk about enterprise data storage, there's a huge movement now to kind of get out of the data warehousing business and kind of moving towards more of a Hadoop HDFS model for data storage. It provides a scale-out architecture. I think we're all familiar with the extensible cluster, and as our data grows, we add nodes and to the architecture, and then we can store more data. High availability, Hadoop was built to fail. The fault tolerance is incredible. Its fault tolerance within HDFS is incredible. You set things like configurable replication, where you can create multiple copies of blocks of files, across multiple nodes. So this is important because it kind of gets us out of that. It kind of creates that disaster recovery model for us, where we can have some level of fault tolerance built in to the system. One of the pieces I put up here was talking about HDFS sequence files. So it's the ability to kind of do binary key value pairs. So that's baked into HDFS, and within Spark environments, you can leverage that as well too. If there's that additional level of compaction that you're trying to do on your data to kind of reduce that footprint, you do have the ability to kind of store it in a binary key value pair format, which can ultimately reduce that data size footprint. So I've got, this is a fairly basic architecture slide, but some of the things that we want to highlight here is that Spark should be complementary to your existing architecture. You shouldn't be necessarily ripping anything out to put it in there and it becoming the new sole tool that everybody uses. It should enhance your existing system capabilities. The key thing for me is you should be able to migrate some of your existing analytic workload onto the platform, get it off some of the other platforms that are probably overburdened now at this point anyway. And one of the things that it can do, HDFS can do a great job of, is archival storage. The fault tolerance and just the general low cost are really ideal for archival storage. So the example here is kind of showing, we've got flow data coming into a Silk server, some other tools like IPA, the other enrichment data sources. You guys are more than familiar with this architecture. Ideally, what those things are doing is pushing data into the Spark cluster that you can then perform streaming analytics against it. You can do some of your larger, more challenging graph algorithms against that Spark cluster. Gets it kind of out of the current operational flow and pushes it onto a system that's kind of sitting in parallel. All right, so I wanted to talk a little bit about performance, and some of the, one of the things that you'll hear a lot within the Spark community is, you get 100x performance on your analytics on Spark versus traditional Hadoop environments. I'll go ahead and caution you and say that your mileage may vary on this. Really, what we've seen is we've seen tremendous levels of performance gain, probably more in the magnitude of 20, 30, 40x types of increase. The specific example that they used did rely on Spark Spark's ability to cache data in memory, which kind of gained this performance measure. I think a more accurate representation of performance is they did an end-to-end page rank, 20 iterations over 3.7 billion edges. So what they're doing is they're comparing GraphX to GraphLab and Giraffe. So Giraffe is another open source package that runs a graph database on top of Hadoop, and you can see there that it's got a 2+x increase over Giraffe, and a minor increase over GraphLab as far as runtime. One of the other key things I wanted to throw on there, I didn't want to create a slide just for this, but is Spark right now is the most actively contributed open source community within the kind of the Hadoop ecosystem. So that the graph showing the number of submissions and contributions over the past year. This is important. A lot of the ecosystem is gaining a lot of momentum right now. A lot of people are getting behind it. The number of people that are attending, Spark meetups and Spark conferences and things like that are growing exponentially. We really see this as a huge growth area. I think anytime you get a lot of momentum behind, an open source project like this, only good things are going to come out of it. The developers have been very responsive to providing new features, bug fixes, enhancements, things like that. We talk a little bit more about performance. There was an article where Spark, the guys at Databricks redid the GraphX benchmark on an instance of Apache Spark that they had running. Let's see, that was so. They were able to do it using 206 EC2 nodes, extra large nodes, in 23 minutes. Previous record was 72 minutes by a MapReduce cluster of 2,100 nodes. This is a scale and order of magnitude improvement on not only performance, but on the size of the cluster that's actually doing that's actually running the benchmark. So GraphX is actually a collection of benchmarks that work on. The focus is really sorting 100 byte packages, and I think to a certain degree, this particular benchmark wasn't terribly well suited for Apache Spark, because one of the things that they had to do to comply with the rules for the benchmark is they had to turn off the Spark's in-memory cache capability. So that there's an order of magnitude speed improvement even over these numbers as well too. But to comply with the rules for the benchmark, they had to actually turn that off. All right, so why you should love Scala if you don't already. I've run a number of development teams over the years, developing a variety of types of applications. And one of the core tenets I always stuck to was don't fall in love with a programming language or a scripting language on some set of principles. You should ideally make choices with programming languages that your developers know well, that provide you some level of consolidation across your environments. So I've got a small example here. So this, again, we won't go line by line through the code, but this is a Scala example that does a simple word count against the content of a text file. We have 5 lines of code. So here's the similar example written in MapReduce. And you see, your normal Java set of import statements. You've got page after page after page. So really what it does is it boils down to 5 lines of Scala code versus 57 lines of MapReduce code. That for me is motivation to learn a new programming language. If given the number of functions and features that are kind of built into Scala, it's worth taking a look at. I know we've all been pitched a million times on different scripting languages and different programming languages and environments. So we've all heard that. This is worth taking a look at. It draws a lot of similarities to Java. There are a number of it actually runs inside of a Java virtual machine. So you can do class sharing between your Java code and your Scala code, which can be another way to kind of streamline some of your code and analytics. So I included a slide just with a few resources that I found helpful. The first is the top level Apache Spark project. They've got some good information out there. It's worth taking a look at. The other thing that they have is a lot of sample code in Scala and Python, in Java, whatever your preference is. So it's definitely worth taking a look at. Spark Summit, much like FloCon, Spark Summit does a great job of capturing kind of the presentations and the content that gets submitted, and they actually post that on their website for folks to utilize. There's a dzone reference card on Apache Spark that I actually thought was really good, so I threw a link in there for that. And the other thing I would encourage you guys to do is get involved in the Spark meetups. They occur all over the country. I'm out of the Washington, D.C. area. I think the topic next month is sparkling visualization. So it's how do we visualize data on top of an Apache Spark platform. These meetups are incredibly well attended. I think the last couple in the DC area, the attendance was 200 plus people, which is fairly good. But I would encourage you to get involved in the community. I think one of the big challenges with not only Apache Spark as a big data analytics platform and others is that I think the FloCon community has very unique requirements for big data analytics tools. And I think we need to get involved with these communities and really articulate what our requirements are for these platforms. And that's it. So questions, discussion?
Just one brief question.
Yes.
It's going to show up again in my work.
Okay.
I have a set of, say, 5,000 arbitrary IP addresses.
Okay.
And I want to select the flows that match as source or destination one of those IP addresses.
Okay.
How easy and efficient is a question like that to ask and to implement?
Yeah, so great question, and that approach I would probably have a separate RDD just to contain those IP, much the way we would like a lookup table, right, in more of a traditional RDBMS environment. That gives you a lot of flexibility, so you can have that kind of persist for that level of analysis, and then just do row level matching at that point through and iterate through your data set. I think this environment supports it well, and a lot of the the speed and performance is gained is because everything's in memory.
So you're effectively doing a join.
You are, yeah, yeah. And the nice part is, though, is it's not the term is correct, but it's not as impactful as it was in the RDBMS world, where creating joins, we knew it was a huge performance cost. With an in-memory database, that cost is negligible. It's really it's really fast, and you don't see much of a performance degradation. Okay, next question.
So first of all, I do like Spark, but I wanted to know your thoughts and ideas for how to get past what I think is probably the biggest limitation to Spark adoption is the idea of the Spark context, and kind of what it prevents doing as far as scalability and multiple users, et cetera. And the other part is more, I think more of a passion of mine is for those who don't want to write code in Scala or Java, about the fact that like the Python support is only about half of what the other part is, whereas that's a language that I would bet most of the people in this group will know.
Yeah, so great questions, and so as far as the context. I think this is a challenge, and this is one of the reasons why I implore you guys to get involved in the community. Is that these are unique types of requirements that I would argue not only this community has, but there are others that do. Things like the ability to support multiple users, security, things like that. We need to articulate our requirements to the development community for tools like Spark and others. With regards to, it was an excellent point. Yes, the Python support within Spark today is not as comprehensive as the Scala and Java support. They are working to increase that. I think one of the things that they're seeing is that at the adoption level, I think there are more people that are interested in writing Python code against Spark clusters than are interested in learning Scala. So. Again, it gets down to my preference is to provide if you have analysts and developers that are used to writing in a certain programming language or a certain tool, then you want to try and enable that and make that happen, because you're going to get a better product. And I think what we're going to see is the inclusion of the additional functions and capabilities in Python that exist within Scala today.
Thank you.
Thanks.
So my question is kind of concerning presentation to someone in perhaps like the operational space.
Okay.
And you had a little slide there where your Spark streaming was outputting to dashboards and stuff like that.
Yes.
So I'm just wondering what types of applications are you seeing that are making use of that functionality, and what ones that you would suggest to kind of pursue?
Sure. Okay. So great question. And really the approaches that we're seeing, a lot of the visualization and dashboards on against big data analytics solutions. What we've seen is kind of a retrofit. A lot of environments, starting back in the Hadoop MapReduce days, and even now onto Spark, is what we're seeing is the output of the analytic gets written to either a database or into a structure that the visualization tool can handle. So you certainly still have those methods available to you. If there's streaming analytics that you're doing, you can have that right out to a database that, if you're running something like Tableau or some form of dashboard, can just read data directly out of that database. And then you're still enabling that kind of real-time update view on the dashboard, but you're complying with the proprietary software tool in structuring the data in the format that they can understand it. I don't know that we're going to get around that. I think it's a viable approach. It's fairly simple when it works. The challenge is that given the number of visualization vendors out there, the methods that they have to look at data, they're all embracing Hadoop. A lot of it's been through a MapReduce paradigm. We're starting to see now a lot of the visualization vendors supporting some form of Spark code to run against a cluster. So it's a matter of time. They'll start to support those things, but I think at its core, we still have the ability to kind of output data into their format and just comply with how they need to see the world.
Thank you.
Thanks.
Hi. I noticed on your slide where you had network flow, excuse me, and Silk specifically, that you were preparing the Silk data for processing by Spark by transforming the data to text.
Correct.
And I was wondering, is that only because we don't publish the formats of our files, or does it actually have to be text?
No, so it actually doesn't have to be text. So that's probably more of a simplistic view. So the key really is are you using it just purely for storage, or do you want to do analysis on the data? And if you do want to do analysis on the data within within Hadoop or Spark, the ability to translate that binary data is key. And currently today, outside of HDFS sequence files, there's no ability to translate binary. So if it doesn't do the binary conversion itself, it doesn't have a way to translate it back out. So ultimately, what you would have to do analysis is, if you were storing in just kind of a raw binary format, you would have to pull that data back out somewhere, put it on a disk, and then run Silk tools against it or something like that.
Okay, thanks.
Thanks. Okay, thank you guys.